That's it. I want to go fairly fast because we do have a time schedule. So you don't have to read who I am or what my PhD supervisor said or the wonderful advice he gave me. I want to concentrate on this bottom line. I think that the fundamentals of Bayesian analysis should be very simple and accessible to school children, and I think that computing it should be equally simple. And that's what I'm trying to get across. I want things to be obvious. First, I'm going to skim through what I think the foundations of Bayesian theory are, and I'm going to use that mode of thinking as a guide to how to compute it, because I want there to be well, symmetry is the wrong word, synergy between what the problem is, how we look at it, and how we compute it. There should be two facets of the same sort of mental processes. The first part of the foundation is that we're thinking about some sort of stuff, and we can put stuff together. This is pretty much application free. You can be thinking about apples or oranges or dollars or whatever. And there's a combination rule, and there's an ordering. Stuff and stuff combining, you put the brackets anywhere. That's a generic concept which is very often holds. And ordering, if x is bigger than y, that remains true if I add something else onto them. Very simple, generic things. It follows from that we get a sum rule. There's no continuity or differentiability involved in this. I can, of course, transform the sum rule to be something else if I want, square it or log it or exp it or something. And I could even make that discontinuous or non-differentiable, as long as it's monotonic. But I can always revert to that. And other things like commutativity just follow. The second facet of the foundations is independence. The idea that I may have some problem to do with horizontal stuff and another problem to do with vertical stuff, and they're independent. I want to be able to construct a joint problem by putting them together and processing them together. There shouldn't be any difference if the problem really does separate. It should separate. And symbols get a bit messy and fussy because there are two different symbols coming now. But that's distributivity. That just says that stuff plus stuff remains stuff plus stuff, even if it's got another coordinate attached to it. And direct product is associative as well. And those two, given that conjunction is additive, give you a product rule and positivity. And that's measure theory. That's the foundation of measures. Very simple symmetries and nothing else. Well, that work and the next, let's move on to divergence. Before we get on to probabilities, I'm just talking about stuff now and distributions of stuff, measures in other words. We want to be able to navigate. We want to be able to move from one measure to another. Whether we do this geometrically or whatever is up to us. But if we're going to program, we need to take some initial state or belief or whatever and modify it to something else. And that modification should be part of the quantification. Look for a variational principle, variational potential, and you find that it must be of this generalized information form, the thing that hasn't, Now there's something rather special about this. It is inherently compressive. If you start at 0, you better end at 0, otherwise you get infinite distance. It's asymmetric. It's compressive. If you annihilate a cell, annihilate something, you can never get it back. And what this means is that there is no natural distance in this space of measures. Because the only connection happens to be asymmetric. And any symmetric connection would have to be in the class of connections, and there is no symmetric connection. So although we can look locally and get a local density and local thing, everything looks right, you better be a bit careful not to integrate up geodesics, because if I do have problem A and some sort of geodesic path and I'm using in my procedures, and I have problem B and other paths which I'm using in this space for my procedures, and I put them two together, the geodesics on a large scale interfere with each other. So this focuses my mind on the things that I'm allowed to do. Probability. Probability, all we need is a sum rule, which you know already because we're thinking of probability of stuff given something else. So the sum rule comes for free because probability is a measure on its first argument. And if I have a chain rule for, associative chain rule, that one, then we get the product rule just with the same algebra as before. And the usual range, the 0-1 range and everything follows for free. So it's very simple foundations for measure and probability. And of course, the corresponding variational potential is the special case of what we had before, because P and Q, the source measure and the destination measure, probabilities are both measures, so that's that. Again, H is compressive. Now, we want to do Bayesian stuff, at least I want to do Bayesian stuff, and I deal with probabilities, and it is very central, it comes from the elementary formulas, that what we can do with probabilities is compressive. And I'm saying this over and over again because I think it is both simple and central and important. If a probability is annihilated somewhere, it stays naught irrevocably. Time's a bit short, so I'm not going to slag off the statisticians to talk about this. What I want to do is summarize the foundations before I get onto the real meat of what I want to say. Simple, basic symmetries that any school child, well, bright school child can understand, imply simple basic equations, the standard ones, very fresh. Other stuff comes for free, but be careful with over-interpretation. Another grumble I have with putting Fisher geometry on a manifold of distributions is that the manifold may not be differentiable, and in any case differentiability and continuity more weakly is an unobservable property. I can never get the infinite amount of information that would tell me whether a function was actually continuous on a small scale or not. And if I can never observe something, I don't want it in my theory. Because if I broke the condition, that would open the door to a different theory. I don't want that. Anyway, I want simplicity, and total simplicity gives me generality, and it gives me power. And that's what I want, my lifeblood. The last preliminary is some remarks on dimension, which is often held to be cursed, the curse of dimensionality. Well, it's not as bad as all that. When stuff adds up, the means add up and the variances add up, and things actually get better with big dimension. So we shouldn't be too scared of this. Equally, although I remarked that the sum rule could be moved around, you could log it or exp it and change the axes, regraduate, regrade, when you get up to big dimension, it is pretty obvious that the standard addition is what you want, because this is basically the central limit theorem. And if you do something like exponentiate it, well, I'll leave it to you to think about what that sort of stuff looks like. The quantiles of this. Totally bizarre. Now, it does look as if you have a problem in large dimension because measures multiply and the numbers get enormous. Okay? take logs. That's what has been going on in statistical physics for 100 and odd years. If we want to deal properly, efficiently, with high-dimensional problems, go to the people who've done it before, the people who are quite happy with 10 to the 24 dimensions. That's statistical physics. And it gives an entirely different outlook on what you're trying to do. If I have a standard mole of gas molecules, 10 to the 24 molecules, with an energy of 10 to the 24 units, kTs, whatever. And there'll be fluctuations, there'll be root n fluctuations on that, but the root n fluctuations are only 1 part in a trillion. They don't matter. The corresponding analog in inference is the log of the Bayes factor. The omega, that would be the evidence. You log it to get Bayes factors or log evidence. And if you're dealing with a problem that's a million dimensions, it's not going to matter whether you get the log Bayes factor right to within a factor of 1,000. Factors of e to the 1,000 aren't going to matter. So don't worry too much if it's going to be very expensive to get your two different models compared to within 60%. The world isn't like that. If you've got a million pixel image you're trying to model with different models, those different models will have very, very different evidences. So you don't need to worry. Okay, Bayes in theory. The standard prior times likelihood inputs give evidence times posterior. I would just like to remark that the evidence logically precedes the posterior, which has got an evidence in it. So, if you try to look at what the symbols are trying to tell you, the symbols tell you first do the integral of the joint, then divide it out to get this. I was taught statistics without Z at all, but just with the proportionality here. Oh, terrible. I've missed out the prob of x given data on that one. I do apologize. X given data. There's always something wrong when you do slides. Anyway, the first task is to evaluate the evidence, and that's what I want to concentrate on now. How do I do this? The only problem is that if we have a million constraints, the posterior is going to be x to the million times smaller than the prior, and x to the million is a bit of a big number, so we'd better be careful about how we deal with it and how we take logs. In practice, we have some sort of complicated likelihood over the prior domain. But one of the symmetries we get for free in probability and measure theory is commutativity. We can move elements around, shuffle them. And I can shuffle them, in principle, by likelihood value. I can, one could, if one was God, do this. In a big problem, it would take a very long time to do it on your own computer, but there's nothing mathematically wrong with doing this. And then, if I have a monotonic curve to integrate, that's really fairly straightforward. Trapezoid rule. Anyone can do that. Now, this is a very special case. It could be my problem. Any general algorithm has got to work in this case. If an algorithm can't do this, then it's pretty useless. But the thing I'm integrating is evidence equals integral of likelihood d volume. At every sample point, I know the likelihood, just work it out. The central issue in getting the Bayesian evidence is estimation control of volume. L is fine, it's volume. I can talk grandly about shuffling stuff around so that it all comes out in the nice right order, but how exactly do I do that? Well, I I think it is pretty clear from logical thinking that that's what we want to do. The question is how to do it. This is the aim. Get a set of samples of points and just add up the evidence as a sum of areas. Break down the range, prior range, 0 to 1, as some sort of line volume is what I'm calling it. It's actually prior mass. And just work out each strip as an average likelihood times the width. Again, though, the problem is that the compression is huge. And what that means is that the last diagram was a bit optimistic. The picture is really more like this, where the likelihood goes up to some huge value that wouldn't even fit into the universe, within some tiny width, that says tiny down there, that's far narrower than the width of a proton. So difficult to draw accurately on a slide. Almost all the volume has almost no mass. And it's the mass, the area of this, or whatever you want to call it, that we want to evaluate. Originally, at the beginning, where all we really know is the prior, all we can access is the first 2 or 3 or 4 powers of E down on that. We can't find any fine structure at all. We can have a look, and by putting in sort of 3 samples, you can get down 1 power of E. By putting in 8 samples, you can get down 2 powers of E, and so on in volume. If I put in 20 samples, each of them will have a volume of E to the minus 3, and so on. And I can do this, and I can do standard Monte Carlo at the beginning, put 20 points down, and get some sort of estimate of what's going on, which will have no connection at all with the spike that I'm trying to find. And that lack of connection will continue for 10, 20, 30, 40, 10,000, 100,000 orders of magnitude until I finally come down to the million orders of magnitude that I'm interested in. A corollary of this is that as I somehow iterate down and move down from what I can access to what I want to access, nowhere along there do I have any idea at all of what's going to go on with the likelihood. It follows from that it is a mistake to try to anticipate down here as I iterate down. It is a mistake to try to anticipate what that spike will be, because I won't know. I have no information on it. And it follows from that I should not try to modulate whatever happens as I come down with the likelihood in the hope that I'm somehow connected to what the final answers are going to be. Because if I modulate by the likelihood and say that the low likelihoods are actually more important than the prior, because I know the likelihood's bigger there, I'll mislead myself, because that modulation doesn't tell me anything about what I will finally want. So I think the only way of staying safe in this environment is to be as simple as we possibly can and not modulate by likelihood at all. And this makes algorithms much simpler, much easier. Have a look at this. Let's start at the top with 8 samples in the interval 0 to 1. 8's a nice sort of number because it's divisible by 2, really. There's an inner half in the first half of the volume, and there's an outer half in the outer half. Now the trouble, what we're avoiding, is the spike right down at 0. The top half's going to be fine, so just peel them off and use them. That top half will contribute the average likelihood of those 4 points times a half. to the evidence. That's easy. So we've done half the work in volume terms. We've used these samples now to throw them away, but I've got to have an iterative scheme, so resample, repopulate the ensemble, take these points, jiggle them around a bit, however you like, to get 8 points in the second half, from 0 to a half, in the inner half. Do it again, peel off the top half. A quarter times the average of those 4. Do it again, keep going, and going, and going, and going. And you get geometrical compression. Now, the problem with doing that is that you don't know, in general, how your space is carved up in volume, and you can't really draw the median contour. You don't know where it is. But that doesn't matter, because pretty certainly the half is going to be somewhere around the 4th or 5th intermediate point. So simply the act of ordering these points, which were uniformly distributed, has shown you where the middle is. So just use the middle as a randomized proxy for a half, and then for the next half, and then for the next half. And hey presto, you've got the evidence. Now you may have to do that 1,000,000 times in order to get down to e to the minus 1,000,000, but at least you can do it, and you've got a coherent, simple, iterative scheme. And it also has the power that comes from simplicity. Because if I go, which way shall I go? Yeah, that'll be fine. So, we've talked so far as if I just had a simple function from 0 to 1, one-dimensional. Yes, I can transform any problem I have to one dimension in principle. In practice, you can't, you don't directly. But what you can do, have at each iteration, is have an ensemble of n points within some likelihood contour. Originally, the constraint is likelihood equals 0, because I'm on the prior. Everything's bigger than 0. And I will decide to reject a certain number of points, say 3 of them in this diagram, retain 5. I know that those outside, there are 2 points outside, 1 there and 5 in the middle. I know what that compression ratio is. I don't have to find it out by some sort of diffusion process. I know it by construction. The compression, it's a beta distribution, t to the 5, 1 minus t squared. And then if I repopulate 3 new points from those 5, I've now completed an iterate, and I've compressed by some number t, which is coming from that beta distribution, and keep going around and round and round. In fact, the most accurate results are from r equals 1, peeling off points 1 at a time, but this is a prettier diagram. So this gives me an iterative scheme. I don't actually have to do the sorting. I can let the ordering by likelihood do it for me. It just happens automatically. So, and this is a nice example of what we try to do in science. We disentangle different facets of a complicated system, treat them separately, analyze them separately. It helps. This disentangles the compression, the navigation in likelihood value, from the exploration, which now has to be done just in a very simple, unmodulated environment, restricted by a likelihood value only. We got proper control of volume because we know by construction what it is. Okay, it's a random variable, we know what the distribution is. We don't have to find it. And if we're doing 1,000,000 steps, well, we'll get pretty good averages, actually. One thing that's worth noting, this is a very general procedure. This algorithm is not debarred from first-order phase changes. if you put any sort of temperature on this, as is tradition with annealing methods, any sort of temperature will modulate that spike, and your mathematics will tell you that it's trying to look at the spike, but won't actually be doing it, so you'll be making some mistakes. This algorithm, this procedure, won't. So, compression is easy. It is handled by construction. Exploration is the interesting one now. I want to deal with large problems. Okay? Very large problems. That does not stop me from dealing with small problems, of course, because a general algorithm will work in special cases, in particular low dimensions. It'll obviously work on one, because we've been drawing the pictures. A million dimensions is, until you get used to it, a little counterintuitive. You have to think. 5 mins? Bloody hell, no. The deal was that we got up to, I was going to take 50.
Oh, then you have 20.
Thank you. 22. No, I mean, I have 7 more slides. I do have things I want to say. The deal with fitting Michael in was that I had 50, sorry. No, you've got to wait for your banquet. 1 dimension is easy. 2 dimensions is the standard circle. A million dimensions, the radius goes up by root n, so the radius is 1,000. The thickness goes down by 1 over root n, but the step size remains much the same. It's unit step anyway. The problem is you want to get to a distant point, and so there's no way of finding what's in the middle, because that has almost no volume at all. So you want to step around the perimeter, and it'll take you root d steps, root r steps, root n steps rather, to take you from the beginning to the end. Again, I'm very much with Radford that we need to step systematically around this perimeter. Randomness will be much slower. And when n is big, it'll be very much slower. But we have to stay inside this hard shell. These are now 3 repeat slides from last year. I apologize for that, but never mind. Not all the audience is the same. I want systematic motion, and that's best done with specular reflection, bouncing off the edge. Very intuitive thing to do. If you think of the million-dimensional picture I just drew, you just bounce around the edge. And that is done with giving the particle a random velocity and stepping around and try to keep going. This is simpler than Hamiltonian Monte Carlo because there's no internal modulation. But I take my cue and my inspiration from that, and so I'm naming this uniform variant Galilean Monte Carlo because I'm trying to pick up Galilean motion. I can't locate the boundary exactly because I want my steps to be finite. So I do have a problem. I start somewhere, decide where to move, carry on, carry on, carry on. As long as this point is okay, I can carry on. Same velocity, just keep going. If it's not okay, then I'll try to reflect off the boundary. This point is not on the boundary, this point is outside. But nevertheless, if I pick up the local gradient of likelihood, this mirror plane will be a proxy for where the local boundary is, which will be somewhere between the start and this prohibited point. So the boundary will be actually along here somewhere, and try to reflect down to a reflected point. And then keep going. I've done the reflection, and that's fine. Except, of course, that this point too could be wrong. could be outside if I'm unlucky. And in that case, I don't want to reject the trajectory altogether because that would be a waste of time. I want to reverse it. So if proceed, do it, dot, 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 dot. If reflects, okay, do it. Otherwise, just come back. If I'm adding a bit of randomness, I'll come back in a bit of a different direction. If I'm not adding the randomness, I'll just go back to however many time steps I want to the start and go out the other side. So this is all in full detailed balance, whatever n the reflection direction is, and a useful one is anticipating boundary orientation. What I must not do, if reflection doesn't work, is allow myself to stay outside. Remember, we're in a million dimensions. If I go a fraction epsilon outside my region, the volume I'm in is now 1 plus epsilon to the power of a million. And the original volume subtends the solid angle 1 plus epsilon to the minus a million. So I'll be very unlikely to get back. So I must not go outside and hope to get back. It will, in practice, not work. So this is Galilean Monte Carlo, and it's designed for moving around a big volume. Now, I drew a sphere there because clearly, introduce the idea that way. But not all problems are spherical. This was the algorithm for Galilean Monte Carlo, forward motion and then mirrors. And that works perfectly for sphere, because this point, the reflected point, looks just like the input point. It's absolutely symmetry. So that'll be fine. But of course, we're always faced with these disk shapes. I think of disks rather than cigars because I've usually got fewer constraints than dimensions. I've got 1 million dimensions, only 10,000 constraints. That's the sort of ballpark I came from. So these things are disks. You can't see the difference in 2D. Anyway, your algorithm will bounce around constrained by the minor axis, but you want to move along the major axis. And here I'm going to reproduce Radford's talk again. He put in scalings on momenta. I'm calling it a semi-metric S because I'm thinking of what we're doing as actually kinematics and geometrical rather than dynamics and physical. Just basically squash the axes and turn the algorithm around to be an appropriately scaled version. And what's going on is the standard Riemannian space business. Ordinary vectors live in what's called contravariant space, and when you get down to gradients, they're in covariant space, and halfway between, there's an isotropic space. And it's the isotropic space which is where the random direction sits. So that's the basic geometry as a way of bringing these things together. The trick, and I'm not going to waste your time by giving all the trickery in there, the trick is that one can use local information at some preferred point to make S a low-order polynomial in grad L, and basically do all this with a few evaluations of a gradient. It's more expensive than simple V equals the simple Cartesian algorithm, which just requires one gradient evaluation whenever you need to turn around. That's the only cost. This will need several wherever you need to turn around, but you'll need to turn around much less often. Right, this is the last slide, Udo, so I'm not doing too badly. This is a summary. Foundations, I believe, are important. They are very valuable things for focusing your mind on what is productive and defocusing it from what is not productive. Of course, this is all personal. We have our own views on these things. And I actually like people to go off and explore different directions, because then there's less competition for me. Simple basic symmetries are all we need to get probability and stuff. Dimension is not the fearsome ogre that we fear. To be sure, there is space in a million dimensions for a lot of horrible problems. Most problems aren't that horrible. And in Maximum Entropy Data Consultants Limited, we have a little saying that we specialize in soluble problems. A soluble problem can be in a million dimensions. And take clues from the people who have sorted all this out. Bayes, that's just that. Nested sampling, compressed geometry. Okay, you can read all that. What I want to get across is that this is simple, and when you come to grips with it, it should be so obvious. It could be in the school textbooks. Kids could be programming this. I'm not joking. We need not make computational inference a complicated discipline. We can make it very, very easy and still have full power. My thanks to everyone here. Steve, who had introduced me to data and all that. Edwin for strategy, Kevin for symmetries, and Radford Neal for whatever differences of approach we have had in our afternoon talks, for showing the way and inspiring me and producing many of the fundamental ideas that I've worked from. Thank you very much, everybody.
Thanks, John.
For the nice presentation. So, questions, please. Since John stayed so perfectly on time, we have some time for questions.
So, since Radford and John are giving a lecture, we have to ask questions. Otherwise, we're too rude. So I don't actually ask question. Namely, you go back to that. Can you go back to the post-tier likelihood that is step-shaped?
Just tell me when to stop.
Step. Yeah.
Oh, that one. Yes.
Yeah. When you throw the samples, you say half. Let's ignore half. Or get half is the point. How can you guarantee that you can get half?
I don't.
So
all I do is take 8 samples and say that the middle.
Take the middle of the samples. Take the middle of the samples.
Yeah, they're ordered by likelihood, which actually means that on balance that's going to occupy or represent the inner eighth, and then the next eighth, and the next eighth, and the next eighth, and then I'm in the middle, and finally the eighth. So the fact that these things are sampled uniformly with the prior means they represent equal volumes, which means that the fourth one down is pretty much at the middle.
Can you find such an example that you spend 1 million times throw the samples are still within the first end, close to this end? Can you find those examples?
Well, statistically it won't happen, because statistically I know that if I put down 1 million samples and throw away half of them, then I'm going to have a beta distribution and I'll get a half to within 1 part in 1,000, almost certainly.
So, further questions?
Maybe I don't understand your method, but
Oh no, it was supposed to be obvious.
well, what happens with your sampling method if you have multi-modes in your likelihood, so you don't just have
Good
one
question.
area?
Good question.
I'm glad. Maybe I do understand.
I haven't drawn it. So we'll just have to go from this diagram. Suppose there's another mode in there. Okay? It'll be... No, this'll do. The guy's got imagination. There's another mode in there. Now, provided one of the samples is in there, then I'll be sampling both. Okay? Then what will happen? Yes, okay, I will use the... oh, I can't be bothered. Suppose I do have two modes, and I end up with some samples in one and some samples in another. Initially, the ratio will be determined by the volumes of their basins. Okay? But what will happen later is that I'm always throwing away the worst likelihood point. Okay? So, I'll be throwing away the worst likelihood point. And as I move up, one of these modes will get higher than the other. And this one will then be thrown away. Because automatically, points will depopulate from the bad mode and repopulate the better mode. Furthermore, as we progress up there, all these individual points have got their probabilistic masses, so I get a proper weighting of those modes, provided I can do some cluster analysis and recognize which point goes where. But if I can identify points with modes, I get their evidence values estimated automatically. It works. And there's, the Cambridge people have been doing lots of tests of this, and it does work very well, as you'd expect.
But then evolving or finding those new points will be a bit tricky sometimes, perhaps. So if you have like a few points stuck in some mode and your likelihood level is fairly high, there won't be an easy way to, find new good.
That's the point. You don't have to find it. The bad mode will depopulate automatically. The points will drop out of it. And provided the good mode has been found by something, it will just suck everything in and dominate.
So okay.
This is an unbiased procedure.
So I guess you just have to have a lot of, or enough points for the number of modes you have in your problem, and, and you'll be fine for that.
Yes.
So each of those
new
points...
If you want 67 more or less equivalent modes in there, then you'd better have 67 points. But usually, many modes are just related by symmetry or something, and there's nothing in that, so it doesn't really matter.
So the new points come from some MCMC step that...
Oh yeah. To get these points, I'm repopulating an ensemble, and the only way I can do that in practice is to select a random pointer or the outer one or something, and jiggle it around until it becomes a new one, and then do another one and jiggle it around.
And hopefully it's independent.
Well, that's the MCMC thing. I have no answers to that. I can pretty much ensure it'll be distant, whether it's independent or not.
So, do we have further questions? Doesn't seem to be the case, so let's thank John again.